Welcome to Spaceverse, your portal to cosmic adventures. In 1977, two small spacecraft left Earth on a mission that would go farther than anyone could have imagined. NASA launched Voyagers 1 and 2, robotic explorers designed to study the giant planets of our solar system. At the time, no one knew that these spacecraft would still be operating nearly 50 years later. And yet, not only are they still functioning, but they've also delivered one of the most surprising discoveries of modern space science, a so-called wall of fire at the edge of our solar system. This fiery-sounding phenomenon isn't a wall in any physical sense, nor is it burning as we understand fire. Instead, it's a superheated plasma zone with temperatures ranging between 54,000 and 90,000 degrees Fahrenheit, detected at the very boundary where the sun's influence ends and interstellar space begins. This strange and persistent feature, recorded by both Voyager 1 and Voyager 2 years apart, is forcing scientists to rethink what the edge of our solar system really looks like and how it connects to the wider galaxy beyond. To understand why this discovery is so significant, we first need to talk about the heliopause. The heliopause is the invisible threshold where the solar wind, the constant stream of charged particles flowing outward from the sun, finally loses its strength. Beyond this point, the solar wind no longer dominates, and the interstellar medium, the thin gas and plasma between stars, takes over. For decades, scientists assumed this transition was relatively clean and predictable. The solar system's influence would simply taper off, and interstellar space would begin. But when Voyager 1 crossed this boundary in 2012, and Voyager 2 followed 6 years later in 2018, both spacecraft revealed a much more complicated picture. Instead of a simple handoff between the solar wind and the interstellar medium, the probes recorded a narrow zone of plasma heated to extreme temperatures between 30,000 and 50,000 Kelvin, or about 54,000 to 90,000 degrees Fahrenheit. Now, before imagining the spacecraft flying through some blazing inferno, it's important to clarify, this is not heat as we experience it on Earth. The density of particles out there is incredibly low, far less than even the best vacuums we can create in laboratories. That means while the particles themselves have enormous energy, there are so few of them that a human being, or even a spacecraft, wouldn't feel heat in the same way. Instead, what the Voyagers measured were the speeds and energies of these particles, which register as these extraordinarily high temperatures. So how does this wall of fire form? Scientists believe it's caused by a combination of processes. One explanation involves plasma compression. As the solar wind collides with the interstellar medium, the pressure builds up, heating the particles in the process. Another likely contributor is magnetic reconnection, a fascinating phenomenon where magnetic field lines from different regions snap, merge, and release bursts of energy. At the heliopause, this could mean the sun's magnetic field interacting directly with the galactic field, producing the extreme temperatures recorded by the Voyagers. The most compelling part of this discovery is that it isn't just a one-off anomaly. When Voyager 1 crossed the boundary in 2012, its data might have been dismissed as something unique to its trajectory. But when Voyager 2 entered the heliopause 6 years later and observed the same plasma heating, it confirmed this is a real and persistent feature of our solar system's edge. And the surprises didn't stop there. The Voyagers also revealed something unexpected about magnetic fields. Scientists had assumed that the interstellar magnetic field outside the heliopause would be oriented differently than the sun's magnetic field inside it. After all, these fields come from different sources, the sun on one hand and the galaxy on the other. But the data showed the opposite. The fields were aligned, suggesting a deeper and more mysterious connection between our solar system and the galaxy surrounding it. This alignment was a shock to researchers. It implied that either the sun's magnetic influence stretches farther than anyone had imagined, subtly shaping interstellar conditions near our system, or that the local interstellar magnetic field is more organized than expected, adapting to the sun's field in ways we don't yet fully understand. These discoveries reshape how we think about the heliopause. For years, scientists considered it a relatively static shield, a barrier separating the sun's domain from the vastness of interstellar space. Instead, Voyager's findings reveal that the boundary is dynamic and turbulent. It's an active zone where solar and galactic forces meet, constantly interacting and reshaping one another. the plasma heating and magnetic alignment challenge long-standing models of heliospheric physics. They suggest that large-scale magnetic reconnection is occurring, merging field lines on a massive scale and releasing bursts of energy that heat particles to astonishing temperatures. These same processes may also explain the energetic particles recorded by both spacecraft as they cross the heliopause. But why does this matter? The implications are huge, not only for our understanding of the solar system, but also for how we think about cosmic radiation and space travel. The heliosphere, the bubble created by the solar wind, acts as a shield against cosmic rays, which are high-energy particles originating from distant supernovae and other astrophysical sources. If the heliopause is more permeable or more active than we believed, it could change how much cosmic radiation makes its way into the solar system. This, in turn, has implications for astronaut safety on future deep space missions and even for life on Earth, which benefits from the sun's protective bubble. The findings also impact space weather predictions on a galactic scale. By understanding how solar and interstellar forces interact at the boundary, scientists can refine models of radiation levels in deep space, knowledge that's critical for planning missions beyond the heliosphere. The discovery also redefines the very scale of the solar system. If the heliopause is more complex and active than previously thought, its size, shape, and structure must all be reconsidered. Researchers are already incorporating Voyager's data into updated models of the heliosphere, which may look very different from the neat bubble shapes once illustrated in textbooks. And the lessons go beyond our solar system. If our heliosphere interacts with the interstellar medium in this way, it stands to reason that other stars' protective bubbles do too. Studying these processes offers valuable insight into how stellar systems across the galaxy shield their planets from cosmic radiation and interact with their galactic environments. Looking to the future, NASA is already preparing the next mission to study these mysteries. The Interstellar Mapping and Acceleration Probe, or IMAP, scheduled for launch soon, will build on Voyager's discoveries. With advanced instruments designed to study how the solar wind interacts with interstellar space, IMAP will provide crucial context for the Voyager's data and help decode the complex physics at the edge of the heliosphere. At the same time, engineers designing future interstellar probes now have new factors to consider. Spacecraft crossing the boundary must withstand conditions of extreme plasma heating, magnetic turbulence, and particle acceleration. These aren't just abstract scientific puzzles, they're practical engineering challenges that must be solved for humanity to one day explore beyond the solar system. All of this underscores the remarkable endurance of the Voyager mission itself. Launched in an era before personal computers, smartphones, or the internet became part of daily life, these spacecraft are still operating nearly 5 decades later. Each year, NASA has to make difficult decisions to conserve their dwindling power, shutting down instruments to extend their lifespan. Yet even now, critical systems are expected to remain operational through at least 2026, continuing to send back data from a region of space no human technology had ever reached before. And perhaps that's the most inspiring part of the story. These probes, carrying golden records meant to represent humanity to the stars, are not just drifting relics of the 1970s. They're active explorers, still rewriting our understanding of the cosmos. Their discoveries raise profound questions. How far does the sun's influence truly reach? How does our galactic environment shape the solar system we call home? What other surprises lie just beyond the boundary of the heliosphere, waiting for us to uncover? Nearly 50 years after launch, the Voyagers continue to redefine space science. They've revealed a dynamic, fiery boundary at the solar system's edge, uncovered strange alignments between solar and galactic magnetic fields, and challenged everything we thought we knew about our place in the galaxy. The answers are only just beginning. Stay curious, stay inspired. This is Spaceverse.